We're Group 16, and we studied the multidisciplinary nature of solar farms. Electrical engineers are the backbone of creating solar farms. Electrical engineers are responsible for the components of the solar units that convert the sun's energy into power. Then, this power must be stored, quantified, and distributed. Electrical engineers create PV models, like shown on the slide, and design the system that will create and move this energy. Solar power fluctuates depending on the weather, and this variable output must be converted to a fixed output that is suitable for the power grid. After analyzing the power output, this can be compared to the theoretical output to determine efficiency and decide where efficiency can be increased. Electrical engineers are important to have around as they understand how electricity is created and how to ensure the system is behaving as expected.
So while electrical engineers may take the spotlight, mechanical engineering is always very important. So when it comes to the production of these panels and the entire system, mechanical engineering is important for like the automation of this industry. So machines, tools, and any sort of thing that involves like hands-off production. When it comes to the power producing, we know that AC-DC converter involves some sort of spinning. So once again, the development, not just the production of these panels, relies on mechanical engineering. And finally, in order to place these panels like where we desire, we rely a lot on transportation, which once again is backed by the mechanical engineering industry.
Materials engineering is an integral part of solar energy. They're responsible for imagining and creating new, innovative ways to incorporate solar technology into almost everything. Part of their responsibility is to make sure that the materials required to make solar tech are actually more sustainable than the mining and use of fossil fuels. If the components of a solar panel require just as much mining of finite resources without improving in efficiency or longevity, then the integrity of the renewable energy source is put in jeopardy. Another part of their responsibility is finding new ways to incorporate solar into already existing infrastructure and daily objects. A Michigan State materials engineering researcher created glass panes that can be used to produce solar energy. This is an example of the future of solar engineering, where ordinary objects like laptop bags can produce energy through solar. All while trying to accomplish those goals, a top priority for materials engineers is producing cheaper and more easily producible solar cells. A lot of research is currently being put into replacing silicone-based cells with organic polymer, a cheaper and more flexible alternative.
Solar farms are essentially large collections of solar panels in a single area. And solar farms can be installed for industrial purposes or on a smaller scale, like in communities. They can create large amounts of clean and renewable energy and can help us reach carbon neutrality. However, installing large amounts of solar panels as well as storing and delivering energy can be quite expensive as well. Solar farms have to be placed in areas that receive significant amount of sunshine, such as the Middle East, Africa, or Central or South America. And solar projects are not always approved by governments, and even if they are approved, they can be subject to corruption.
So for solar energy to be made more efficient, it not only has to be efficient in scientific terms, but also in economic terms, or no firm would commit to implementing the technology. In environmental economics, for a form of technology to be considered truly efficient and clean, it has to, 1, generate the same service and function at a similar or better rate and quality, 2, be environmentally superior to the current technology, and 3, be cost competitive without government subsidies. The first two standards can be met by engineering disciplines, but we would require the help of economic analysts to pass the third standard. We must conduct a cost versus benefit analysis to see not only if, but also how long after implementing the technology will it become the superior option, because this will be the ultimate barrier to actually implementing efficient solar technology as opposed to developing the tech only to have no firms take the project because it simply isn't financially and economically feasible.
So, as we can see, in order for this project to be accomplished, it requires the collaboration of lots of different people, demonstrating why engineering at heart is a multidisciplinary field. Thank you.